In this video, we're going to talk about radioactivity. So far, we've learned that every element has a different number of neutrons and protons, and even within the same element, sometimes they have a different number of neutrons, and we call those isotopes. Basically, an element is deemed radioactive if it doesn't have the correct ratio of neutrons to protons. In this diagram here, we have a 1-to-1 ratio of neutrons to protons represented by this line. And the shaded area is called the band of stability. Essentially, if an element is within this band of stability, it is not radioactive, it is stable. However, if it's outside of it, it's going to have to undergo some process to become stable again, and that process is radioactivity. There are going to be three major types of radioactive decay that we'll discuss. Those three are alpha decay, beta decay, and gamma decay. Here are your three basic types. Starting with alpha, it's given the symbol from the Greek letter. The symbol, when we write our radioactive equations, is going to be 4,2He, so just like our atomic symbols, where we have the mass number, the atomic number, and then the symbol. So in this case, if we have a mass of 4 and an atomic number of 2, that is indeed helium. But it's just the nucleus of a helium atom. Therefore, it has a +2 charge. Now, this is relatively big compared to the other decay particles, so it has very low penetrating power. It can be stopped by paper or clothing, as you can see in the diagram down here. Our next type of decay is called beta. It has 0 mass and a -1 atomic number, and a symbol E, because this is just an electron. It has no mass compared to the helium atom, so no neutrons or protons. It has a -1 charge. The reason we put the -1 down here is so that it balances out in the equations, as you'll see later. Since it's an electron, it has a -1 charge compared to the +2 of the alpha. And being much smaller than the alpha particle, it has moderate penetrating power. It can be stopped by metal or wood, or it will be stopped by your hand. Last, we have gamma decay. We all know what happens when you come into contact with gamma radiation. But gamma radiation is indeed just that, very high energy radiation, and despite movies and comics, does not turn you into a green superhero with super strength. It has no mass and no atomic number because it is just energy. It's not actually a particle at all. It's represented by this Greek letter gamma, sort of looks like a Y with a loop at the bottom. Being as it is not a particle at all, so no protons, no electrons, it's going to have 0 charge, and it has very high penetrating power. It takes a lot of concrete, several feet of concrete, to try to contain gamma radiation. This is why at nuclear power plants, you see the silos surrounding them. They are made of very thick concrete, such that in the case of a nuclear meltdown, it can contain the gamma radiation. You'll see several questions asking you to compare the energy and the mass of the various radioactive decays. So in terms of energy, gamma is the greatest, beta is next, alpha is the lowest, which I already indicated here. And looking at the mass, notice that it is inverse to the energy. So the more energy, the less mass, and vice versa. Alpha is the biggest, having a mass of 4. Beta is the next. We say 0 because that's 0 AMU, but it still has a very negligible weight, about 1,800 times smaller than the proton. And then gamma is last with no mass at all. One other note I want to make, after element 83, so looking at our periodic table, from polonium and on, all elements are going to be radioactive. Before that element, it depends upon the isotope. For instance, carbon-14 only has an atomic number of 6, but it has too many neutrons, so it will undergo radioactive decay. So here is a nuclear reaction equation. Here we have element 86, radon. Notice that it is after bismuth, so it is radioactive. It has a mass number of 222 and an atomic number of 86. It is going to undergo alpha decay. So it's going to give off this alpha particle, meaning it will lose 2 protons and then the 2 neutrons to make up the rest of the mass. Whatever's left over is going to become a new element. So if we subtract a mass of 4 from radon, we're left with 218. And if we subtract an atomic number of 2 from 86, we get 84. So we're going to treat this arrow or yield sign as an equal sign. And we just have an equation saying that this mass equals these masses, and this atomic number equals the sum of these atomic numbers, which is everything that's stated here. So in order to figure out if I gave you one of these missing, you would just have to use basic algebra to figure out the other missing particle. Here we have beta decay. So we have thorium at atomic number 90. Thorium is going to undergo beta decay. In doing so, it gives off a mass of 0. So this mass is the same as that. But the atomic number is -1, meaning that for the remaining particle, the atomic number has to go up to balance out. So when thorium at atomic number 90 gains a proton from this beta decay, it becomes protactinium. So what happens is one of these neutrons will actually split into an electron, given off as the beta particle, and a proton. So that's where this extra proton comes from. And of course, since we changed the protons, we changed the element. Finally, we have gamma emission. Now, gamma emission does not involve the change of mass, so we'll still have the same element. But what occurs with the gamma emission is that the particular isotope is metastable, meaning it has too much energy and it has to release that. So anytime you have something that's metastable, you'll see a lowercase m here next to its mass number, and that will undergo gamma radiation, and none of the numbers change because both of these are 0. So if I were to ask you what type occurs, all you'd have to do is look at the decay particle. Here, we know that that is beta. In number 2, we identify this as alpha. And number 3, we see that, and that is gamma. So that way is easy. Now here, I'm going to have you fill in the missing particles. So for the first one, remember that this mass on the left side of the arrow has to equal the sum of all of the masses on the right. This atomic number must equal the sum of the atomic masses over here. So 218 minus 218 gives us 0 left over. 84 minus 85 means a -1. Notice 85 plus -1 will give us 84. Since this is 0 and -1, we know that's a beta particle and has the symbol E. Here, same element, we have an M to dignify that it's metastable, so no change in mass or atomic number, and that is gamma. Here we go down in mass by 4, so we have 4 left over. Difference between these is 2. 4 and 2 means it is a helium nucleus, alpha particle. And finally, no change in mass, so this is a 0. We're increasing our atomic number, so we had to give off a beta particle. Remember, masses on the right side equals mass on the left. The sum of atomic numbers on the right equals the atomic number on the left. Basic algebra here. In terms of radioactivity, two terms you might have heard more often are fusion and fission. Fuse, of course, means bringing together. So in fusion, we're going to bring two small nuclei, which is just the plural of nucleus. We're going to bring them together and form something larger. And in this case, this is going to release an extreme amount of energy. So this is in fact the reaction that occurs in our sun. Hydrogen atoms will combine to form helium. Notice once again, the nuclear equation balances out. We have mass of 2 and 2 from hydrogen. It's going to yield 4 for helium. And the atomic numbers will add together and be 2. So 4 and 2 makes it a helium nucleus. Here's also a picture showing deuterium and tritium, the different isotopes of hydrogen, forming helium. In this case, an extra neutron would be produced as well. Now, the nuclear reaction that occurs in nuclear reactors that we use for electricity is called fission. As the opposite to fusion, fission is taking a large element and breaking it apart into smaller ones. This doesn't really release quite as much energy. However, we can still use that energy to create heat, and that heat then boils water. Boiled water turns into water vapor, which rises, and that spins turbines, which powers generators. That's how we use nuclear energy to create electricity. So in this case, we're going to take uranium, we strike it with a neutron, so a mass of 1, no atomic number. We use N as the symbol for neutron. So this neutron is going to hit the uranium at high speed and essentially break it apart. So it forms two smaller particles. This is the fission part. So we have a barium and a krypton. Balancing out the masses, over here we have a total of 236 mass. So if you add 142 and 91, you'll notice that we're missing a mass of 3. So in this case, we're going to have 3 neutrons that then get to go more into the reaction. Our atomic numbers on both sides of the equation will add up as well. So this uranium was broken apart by a neutron in the first place. So these neutrons that got created will then go find their own uranium atom to strike, and this will keep occurring. Each of these 3 reactions will then produce a total of 9 neutrons, so on and so forth. So this is called a chain reaction. So in nuclear reactors, they have to use things called control rods, which actually absorb these excess neutrons so that they can control the speed of the reaction. Otherwise, too much energy would be produced too quickly and things would heat up, and then that leads to a nuclear meltdown, which is not good. In the next part of this unit, we will talk about half-life, which is how long it takes for any of these radioactive samples to split.